In this video, I will discuss the two most common network models, the OSI model and the TCP/IP model. This video will cover CCNA Objective 1.1, compare and contrast OSI and TCP/IP models. As you're probably aware, networks are complex systems of protocols, software, and hardware components that function together to transmit data from a source to destination. We use network models to visualize the network communication process in a more simplified and easier to understand way. Network models break down the communication process into standardized functional layers. This standardization allows vendors to make products that work together. It allows for modularity so that changes to one layer in the model do not impact the other layers of the model, either above or below, and it gives network operators a common language to describe network functions and capabilities. There are two types of network models. There's protocol models like the TCP/IP model and reference models like the OSI model. Both models break the network communication process into functional layers, 7 layers in the OSI model and 4 layers in the TCP/IP model. Let's start a deeper discussion with the Open Systems Interconnection or OSI model, which was published in 1984 by the International Standards Organization. It is important to memorize the 7 layers of the OSI model in order by both their name and by their number. Now you can use mnemonics to help you remember the layers in the proper order. Going from the top down, try all people seem to need data processing, or from the bottom up, you can use please do not throw sausage pizza away. Next, we will discuss each layer in detail, starting with layer 1, the physical layer, and we'll work our way up through the layers. For each layer, I'll give you some key facts and attributes that you need to remember. Layer 1 is the physical layer, which defines the physical characteristics of the network medium. This includes the type of media, like radio waves, fiber optic cable, copper cables, the types of pin connectors that are used, as well as the voltages that's used. Devices that we associate with the physical layer are hubs, repeaters, and network interface cards. Next, there's layer 2, the data link layer, which is responsible for forwarding frames on the network. It also defines the protocols used to exchange data over a specific type of network or over specific types of network media. Layer 2 protocols include Ethernet, Token Ring, HDLC, and Point-to-Point Protocol, or PPP. The data link layer also includes the functions of error detection and retransmission of frames, as well as Ethernet, or what they're also known as MAC addresses. The devices we associate with the data link layer include switches and bridges, which forward Ethernet frames based on the destination MAC address. The data link layer is the only OSI layer that itself has 2 sublayers, the Logical Link Control sublayer, or LLC, and the Media Access Control sublayer, or MAC. The LLC sublayer is responsible for interfacing and negotiating parameters with layer 3, the network layer, and the MAC sublayer is responsible for interfacing with layer 1, the physical layer. Next is layer 3, the network layer, which is responsible for routing packets between logical networks. Network layer protocols include IPv4, IPv6, ICMP, which is the protocol used for pings and trace routes, and of course, all of the routing protocols such as RIP, EIGRP, OSPF, and ISIS, and of course BGP. Network layer devices are routers, which use IP addresses to forward packets to destination networks. Layer 4 is the transport layer. The transport layer is responsible for segmenting data streams into small pieces called segments and adding a sequence number to each segment so the segments can be reassembled by the receiver. Flow control and end-to-end reliability, if required by an application, is performed at the transport layer. Port number addresses are used at the transport layer to deliver segments to the proper application. The 2 protocols that we associate with the transport layer are TCP and UDP. Layer 5 is the session layer. The function of the session layer is to allow communication between applications and to establish and end sessions between those applications. Application Program Interfaces, or APIs, such as NetBIOS, Remote Procedure Calls, or RPCs, and TCP/IP sockets are used at the session layer to allow applications to achieve high-level communications over the network. Next, we have Layer 6, the presentation layer, which is responsible for the presentation of data to the end systems if required. An example is translating between different encoding methods, such as ASCII and EBCDIC, so that different types of computers, such as PCs and Unix machines, can communicate over the network. Also, compression and decompression, if needed by an application, are handled by the presentation layer, as well as some types of encryption. An example would be secure socket layers, or SSL. The services provided by the presentation layer are not always needed by applications. So, if an application does not need the services of the presentation layer, then that application can communicate directly with Layer 5, the session layer. Finally, we have Layer 7, the application layer. The application layer does not refer to the actual end user applications themselves, but rather it provides services to those applications. For example, web browsers are not at the application layer, but the service a web browser uses, such as HTTP, is at the application layer. To visualize the communication process from sender to receiver, it's important to remember that each layer represents a process running on a computer, and those processes communicate logically to their peers on the other computer. So in order for a protocol to work, it must pass its data down the layers from application to physical layer, layer 1. The data is then transmitted over the physical connection to the other computer, and then is passed up the stack of layers from physical to application to the receiving application. Each protocol uses something called a Protocol Data Unit, or PDU, for transmission that includes a header with information required by the protocol and the data being transmitted. As data comes down from an application, each layer takes the data and adds its own unique header. The data link layer adds both a header and a footer, which is called encapsulation. So at the data link layer, the data is encapsulated into a frame for transmission. The PDUs at layers 4, 3, and 2 have specific names that you'll need to remember, and those names are segment, packet, and frame, respectively. Finally, all of the layer functions we just discussed with the OSI model are addressed by the TCP/IP model, but instead of breaking them down into 7 layers, 4 layers are used. Now, it's important to understand how the OSI model layers compare to the TCP/IP model layers. Note that the functions of the top 3 OSI layers, application, presentation, session, are performed in a single TCP/IP model application layer. The transport layers of both models perform the same functions of segmenting, flow control, and end-to-end reliability, and the TCP/IP internet layer is similar to the OSI network layer and performs routing of IP packets. The network access layer focuses on how the bits are transmitted over a given link, much like the data link and physical layers of the OSI model.